Section 4.5, analyzing lines of fit. In section 4.4, I told you, we can use technology to create, to do things much more efficiently and much more accurately, and we're going to do that in this video. So we talked in section 4.4 about correlation, scatter plots, and then what we're going to do here in section 4.5 is we're going to actually, make some determinations about this data and figure out an equation to model a set of data that you're given. And that's going to be really, really cool with what we can do with that information. Got a couple of vocabulary terms here to start. Line of best fit. It's a line that models that best models a set of data, and there is an exact answer for these data sets for a line of best fit. We're going to use the technology to do that. Okay. The process of finding the line of best fit is called linear regression. Okay. The calculator, or in this case Desmos, that's going to take care of all of it for us. We just need to tell it to do it, and it will do it for us. And then the final vocabulary term here is correlation coefficient, at least the final vocabulary term here for a little while. Correlation coefficient. It's a number. It's defined by the letter R. It's always going to be R, ranging from -1 to +1, that describes how well the line of best fit models the data set. Okay, it's never going to go outside of -1 to +1. It's always going to be in between there. Okay, let's talk about this correlation coefficient here for just a second. So we got this range from -1 to +1 that describes how well the line of best fit models the data set. If your correlation, these are R values, if your correlation is close to 1, okay, or as your correlation coefficient gets closer to 1, so maybe it's going to be like 0.8 or 0.9, or getting closer to 1. As you get closer to +1, what you're getting is a strong, whoops, let me retry that, scroll back up, strong positive correlation. Strong positive correlation. If we had R equals 1, is what happens then is a perfect line. Okay, R equals 1 is a perfect line with positive slope. Okay, R equals 1 is a perfect line with positive slope. When we're talking about people, if your data set is determined, is using or referencing people, I have never seen an example of a correlation coefficient of 1, because we're all different. We all do different things, even though we do a lot of similar things too. Okay, we might weigh the same, but we'll have different heights, or we might be the same height and weigh differently, or we might spend the same amount of time studying and have different test scores or GPAs or something like that. People usually are not linear. Okay, we don't fall into perfect lines, but we do have strong positive correlations in a lot of things. Is our correlation coefficient, or as our correlation coefficient gets closer to -1, again, that's a strong correlation. But in this case, let's try that again. That's an S, strong negative correlation. Strong negative correlation. Okay, and then if we had R equals -1, that one is a perfect line as well. But that one would have a negative slope. Okay, so the closer you get to 1 or to -1, the stronger your data fits a line. The stronger your data is easier to model. As we get into the middle, really anything like -0.5 to +0.5, those are weak correlations. If we were exactly 0, this would be no correlation. No correlation. If your R value is 0, or really even approaching 0, there's no correlation there. That's what that number represents. If we were like somewhere in here like -0.5 to +0.5, that is a very weak correlation, and maybe a line isn't the best way to model that set of data. And we come across that not so much in Algebra 1, but in Algebra 2 we do talk about different types of best fit lines. Sometimes it's a curve, and there's different types of curves, and that maybe fits a data set better. Okay, but for now we're just working with lines, and we're just determining, is it a strong positive correlation, strong negative correlation, no correlation, or a weak correlation, something like that. What I want you to do right now, pause the video real quick, head to desmos.com/calculator, and then we're going to actually use Desmos to figure out our lines of best fit, so we don't have to do anything by hand, and it's really, really pretty simple. So the table below shows the number X of teachers and the number y of students in each of several schools. Okay, you can get the table written down right now if you want to pause the video real quick. Step number 1 says find the line of best fit. So I already made a table in Desmos. You can see it right there. That makes it really simple. Okay, and then what you're going to do is we did this in section 4 where we made the scatter plot. How you do the line of best fit, you're going to enter down into the next box where you can type, and this is what you're going to type: Y1, and then the squiggly, this is the button right above tab. You're going to have to shift, and then the button right above tab, it's right to the left of the 1 button. It's that little symbol, and then MX1 plus B. You don't need to worry about doing any special symbols for the ones down here. The Desmos will do it for you. And the reason we do Y1 and X1 is because our Y values in our table are Y1 and X1. Okay, we just need to tell it which table to use, because if you have multiple tables, you'd have to tell the calculator which variables to use. But we're talking lines, so that's y equals mx plus b. So this is the formula we're going to type into Desmos, and it's going to spit all of this out at you, and it's going to graph the line for you as well. Okay, it's going to do everything for you. All you need to do is tell it what to do. Okay, so it tells you the slope. Here's your slope, 20.6429. Here's your y-intercept, 42.33. And it also tells us our correlation coefficient. It's the r value, not r squared. It's r, okay? So question number 1 was find the line of best fit. Well, Desmos did that for us. It is y equals, scroll back here, 20.64. 20.64. I'm just rounding to 2 decimal places, and then there's an x on the end of that one, and then our y-intercept, 42.33 plus 42.33. Now, X and Y represent people. I don't know how you could have 0.64 of a person or 1/3, 0.33 of a person. That doesn't make sense. So in this case, because we're referencing people, tangible objects, things that you can't have half of, I'm okay if you want to round this to y equals 21x plus 42. That's okay, because, like I said, we're representing people. We can't have 1/3 of a person or 64% of a person. It doesn't make sense. It's not possible. So if you want to round to whole numbers for this example, that's okay. That makes sense. Question number 2, find and interpret the correlation coefficient. Well, Desmos gives us that. It's this r value right here. We can say r equals 0.9595. Well, interpret means just kind of describe it. To me, that's really close to 1. Okay, this is a strong, in this case it's positive, so positive correlation. Okay, now notice this correlation coefficient, that is not the slope of our line. Okay, correlation coefficient tells us how strong and in which direction. It doesn't tell us the slope of the line. That's what the line of best fit tells us. Okay, last thing, interpret the slope and y-intercept of the line of best fit. All right, well, the y-intercept I think might be a little easier to describe first. So the y-intercept, so x represents teachers and y represents students, according to this table. So the y-intercept occurs when there are 0 teachers. So if we were to find this school district, maybe this is a big school district somewhere with a lot of high schools, and we just look at different data points from each of these high schools. If we could find a school with 0 teachers, what this model tells us is that there would be 42 students still in that building, which doesn't make a whole lot of sense. We could say something like, if there were 0 teachers, there would be 42 students. That doesn't make a whole lot of sense. Maybe we can put a couple of question marks. That just doesn't make sense. But that's what the y-intercept technically means in the context of our question, or in the context of our example here. So, sometimes they're not going to make sense, but that's what it represents. The slope. So slope, remember, slope is change in y over change in x. So if I increase my y value by, the x value, because this slope is x. So if I increase by 1, if I increase the number of teachers, what's going to happen then is the number of students are going to go up by 21. That's what this slope represents. It says each teacher added or each teacher added to a school adds 21 students. Something like that. Now, I would say this is a fairly unrealistic example. I don't know what school is going to have 250 kids in it and only 10 teachers. Our high school, AP high school, only has 250 students roughly, and we have like 25 teachers. So obviously this isn't a necessarily realistic example, but this is just data points that we can work with and kind of practice with and try to figure out what these numbers represent. Got a couple more vocabulary terms here for you. Interpolation, extrapolation. These are just fancy ways of saying using a line of best fit and making an approximation or estimation of what's going to happen between two values that we know. Okay, so we're going to kind of go back to that last example here. Use the previous example in line of best fit. Approximate the number of teachers when there are 336 students. Well, it didn't give us 336 students, but 336 students would fall somewhere like in here. Okay, 336 students fall somewhere in here. So now what we're going to do is we're going to use this line of best fit, which again was y equals, 21x plus 42. We're going to use this information to estimate or approximate what would happen if we had this line, if we could find a school with 336 students. So if you remember the y values in our example, the y values in our example represented students. The x value represented teachers. It's asking to find the number of teachers. So we're not going to replace x. We're going to use that 336 and we're going to replace y. So we're going to say 336 students is equal to 21x plus 42. And now it's a basic, chapter 1 type of problem where it's really a two-step equation. You just need to subtract 42. 336 minus 42 is 294 equals 21x. And then divide by 21. And we find that x is equal to 14. That's 14 teachers. Okay? That's the approximation. If we knew the school had 336 students, we could say there are approximately 14 teachers within that school. Okay? Question number 2 then, predict the number of students when there are 20 teachers. So now, again, we didn't know what 20 teachers was, but 20 teachers falls outside of the range that we know, whereas 14 teachers and 336 students falls in between. So inside the data set is interpolation. Outside the data set is extrapolation, just an example of each one. Really, it's the same thing. We're just plugging in a number and finding the other one. Okay, so 20 teachers, remember x is the number of teachers, so now we're going to replace the x value here in our equation. So we'll say y is equal to 21 times 20 plus 42. This is something you can type right into your calculator. If you want to do 21 times 20 first, that's 420 plus 42, and we find that there would be 462 students in that building, which is a huge amount of students for only 20 teachers. No school would ever do that. But we have our example, we have our data points, theoretical data points at that, and we can make some inferences and approximations based on the information we have. Final vocabulary term here is causation. Remember I said correlation is not cause and effect, but sometimes cause and effect is in play here. Causation simply means a change in one variable produces a change in another. It's a strong correlation. It doesn't say positive or negative because it could be either one, but it's a strong correlation between variables. Something like hours spent studying and test score. Because I studied a lot for my test, I did really well. Generally, that's cause and effect. Or because I worked out a lot more, I was able to bench and squat more. My total weight was higher. Or something like that. Okay, causation. I did one to produce a change in another. Okay, so I got 4 examples here. Tell whether a correlation is likely. If so, tell whether there is a causal relationship. That's not casual, that's causal. Okay, does one affect the other? So does the first one cause the second one to change? That's really what it's asking. So question number 1 here, time spent babysitting and amount of money earned. Is there a correlation? Absolutely. Yes, there is, for sure. We can all see that we spend more money or we spend more time babysitting. Generally, we earn more money unless we're babysitting siblings, and then that's kind of an unfortunate situation. But if we're babysitting other people's kids, definitely, this is a positive correlation. Now we need to determine if there's a causal relationship, or is there causation happening? Causation. Does increasing my time babysitting, assuming it's other children, like other families, does my time spent babysitting cause my amount of money earned to increase? Absolutely. Yes, for sure. Yes. More time, more hours equals more money, for sure. Question number 2, the number of banks in a population of a city. Is there correlation? Does the number of banks increasing tend to show a population increase? This one's a little harder to say. I'm going to say possibly. My reasoning would be if Applington got another bank or in addition to Lincoln Savings Bank, would the population of Applington increase? We really can't say that. Maybe it would. I think it would be the other way around. If we increase the population, we might get more banks, but that's not what we're doing. We're trying to determine if we increase the number of banks, will the population go up? Possibly. It would be positive, but we can't say that for sure. The second part, causation. Does adding another bank cause the population to go up? No, not really. We can see that. The other way around, maybe would be causation, increasing the population of a city. If Applington doubled in size, maybe another bank would come to town as well. But it's just hard to say. So I don't think we can say it's causation. Maybe there's correlation, possibly. It wouldn't be a very strong one, because I know towns of 5,000 that have 3 banks and a town of 1,000 or 1,200 that has 2 banks. So it's really, really hard to say. So we can't say there's causation at this point. Question number 3, time spent exercising and calories burned. Is there correlation? For sure. Yeah, definitely correlation. We can see that. Yes, this is a positive correlation. Positive. As you increase your time spent exercising, calories burned goes up. Okay? Causation? Definitely. Increasing your time exercising directly causes your calories burned to go up. Yes, absolutely. And then question number 4. This one's a little tricky. Eating organic food and test scores. Is there correlation? This one would be hard to say. I'm going to say maybe. It's hard to say. We don't know. If it was, I would say it's probably positive. Probably positive. But I don't know that there's any way to track that. Maybe maybe the morning of a test you eat a really good breakfast. Maybe it's not organic, but you eat a really good breakfast, a hearty breakfast or a healthy breakfast that isn't organic, and your test score goes up. Maybe it's just because you're full of energy and you're ready to go, or you studied the night before. I just don't know how we could say there's correlation. And if we can't say there's correlation, then I don't know how we can say there's causation. If there's not correlation, there's definitely not causation. I'm saying this one's a no. Okay. We don't know. I haven't seen any data that says eating organic food leads to increased test scores or causes your test scores to get better. So we'll just leave that one as a no.